All right, 2, 5, limits at infinity. So we switch it up. We're not approaching one specific number. We're going towards infinity or maybe negative infinity. So way out on the ends of the function. And what happens way out on the ends of the function, a lot of times we would approach horizontal asymptotes, or perhaps like a slant or oblique asymptotic flow. So those can happen. All right, so if f of x becomes arbitrarily close to a finite number L, where all sufficiently large and positive x, we write the limit as x approaches infinity of f of x will equal that L. In this case, y equals L is the equation of the horizontal asymptote. Also is the case for the limit as x approaches negative infinity of f of x equals L. All right, so first you got a function like this, has two asymptotes. So this one's L, you can call this one M if you wish. But as x is going this way towards infinity, you're approaching L. As x is going this way towards negative infinity, you're approaching M. To me, this section is actually easier than the previous section. You've learned this before. You've learned techniques and tricks to find horizontal asymptotes, comparing degrees and numerators over denominators, right? It's the same, it's a certain thing if it's bigger, if it's less than the numerator or denominators. So easy example, if I take the limit as x approaches, say, negative infinity of, let's just do 2 plus 10 over x squared. I'm going to use some properties just to illustrate this. You don't have to. But if I would say, break it up into multiple limits, x approaches negative infinity of the first, say, function as 2, plus the limit of the second function, 10 over x squared. And again, this is just illustrating the point. You probably won't go through this. The limit of a constant, no matter where x is approaching. Think about a constant as a flat line, right? So no matter where you are on the x-axis to get up to the function, you're always going to approach that same y value, right? So the limit of a constant for this first part is just 2. No matter if x is going to 1, 2, 5 million, whatever, right? It's always going to stay at 2. Now, when you're going over here, think about this is negative infinity, a negative big number, negative 1 million. squaring it becomes a positive, what, 1 with 12 zeros? Oh, yeah. All right. It's a very huge positive number down here, right? Any number over a very, very, very large positive number goes to 0. Right? Even if it's negative, it's going to go to 0, right? So think about the fractional terms of it. 1/10, right, as a decimal. 0.1, 1/100th, 0.01, 1/1000th, 0.001, right? So it's getting like 0.000001 in the positive, right? And it's only being positive for this particular part because it is being squared. You look on the negative side too. 10 divided by negative 0.000001. That's like, I'm sorry, 10 divided by negative 1 million or something. That's a very small decimal of negative 0.000000. That's just on the other side of 0. It's still going to 0, right? So on both sides, you're approaching 0. So, and then the hardest problem in this class, 2 plus 0 is 3, right? No, 2. No, we're not doing any of that new math. Right? 2 plus 0 is always still 2. All right, let's look at a little bit of trig. Now this one you might be able to just think about it. X in this case, you see is a angle, right? Sine of X, sine of any angle. No matter, there's no restrictions on the domain, right? For the sine function. You can put sine of any angle in there and you can hit enter on your calculator and you will always see a number between -1 and +1, right? So this is because X is the angle, right? Now we got a square root of a huge number. It's still a big number, right? So all right, -1 divided by a big number or +1 divided by a big number. So you got -0.000001 and +0.00001. Both of them are still going towards the same location as 0, right? So this limit is 0. Now, in a sense, what I just did there was the squeeze theorem. I can illustrate this by the squeeze theorem. Know the sine of X has to be between +1 and -1, right? My function there is sine of X divided by the square root of X. Take the limit of each side. So there's no trig function in this. Wait till see, we just did this, right? Square root of a huge number is still a big number. -1 over that huge number is still 0. Limit of this one. This one's still 0, so therefore this limit has to be 0. All right, if I have this expression, x to the n power, okay, as x goes to positive or negative infinity. And let's look at the positive side first. A big number. And if n is positive, a big number raised to a positive number. This is a big number, right? A negative number raised to a positive number. And ends. So like, this, don't even say a big number. Let's just say -2 raised to a positive number 3. -8, right? -2 to the 4th is positive 16. -2 to the 5th. Right? So this is all going to depend whether n is even or odd, right? Let me erase this part and simplify it further. If I go to positive infinity, and n is positive, this is always infinity. Makes sense. If n is even, now specifically n is even, right? So should have put this as positive or negative. The exponent is even no matter if you got a positive or a negative base, your answer is always positive. So this goes to positive infinity. If n is odd now, we got two situations. Limit as x approaches positive infinity of f of x. So a positive number raised to any power is still positive, right? But if n is odd, limit as x approaches positive infinity, negative infinity. So a negative number raised to an odd power is negative. Yes, sir.
So greater than 1, not greater than 0.
No, we could do it in 1. Oh, I'm sorry. You were right. Positive integers. I'm looking at it. I think did I say that and not write it? So I was just trying to do some shorthand and I didn't write the right shorthand. So let's just put, do that. Erase this. N is a positive integer.
Oh, so look back to check, make sure that nothing right.
My hand's getting tired too, so I was trying to write some short stuff. And again, this kind of plays on the conceptual part that we did earlier when we're going to try to put some numbers in. As we're going towards infinity, we want to see what each part of perhaps a polynomial is going to go towards, and then we'll be able to see what the final function goes towards. All right, so polynomial function, p of x. Behavior as x approaches positive or negative infinity. So that's the end behavior. You've heard this before. What is the end behavior of a function? What's happening way out on the ends, right? But if it's for a polynomial, it's determined by the term with the highest power of x. So these are really easy because you don't have to look at the entire polynomial. Just pick out the biggest one, biggest term in there. And then you can plug in positive or negative infinity in it. And that determines the behavior in the entire polynomial. So if I have p of x is equal to 3x to the fourth minus 6x squared plus 6x minus 10, something like that, whatever you wish. I say the limit as x approaches infinity of p of x is the same thing as the limit as x approaching infinity of the power term. That's kind of what it's called, 3x to the fourth, right? X is going to a big number. The exponent is to positive 4, which is even. So that just means it's getting more positive. Times 3 is even bigger, positive, right? So this is just also going towards infinity for that one. All right, so the highest power in there is 3. So we can say this is the same thing as looking at the limit as x approaches negative infinity of just the negative 2x cubed. Ignore the rest. Negative infinity, negative big number, raised to an odd power will still be a negative big number. Times the negative 2 now makes it a positive big number. Positive big number in this class is called infinity, right? Rational functions. These are easy. Y'all have done these before. All right, so you remember what the trick is? Degrees of the numerator and denominators, compare them. First degree polynomial on the top, second degree on the bottom. Rule says if it's smaller on the top than on the bottom, it is always horizontal asymptote, y equals 0, right? So my horizontal asymptote is y equals 0. That is my limit for this. As I'm going to either plus or minus infinity, we'll just choose plus for this one. Let me show you that the algebraic way of doing this is take each term in the numerator and denominator and divide it out by the largest power you see in there. So I have x squared. So I have 3x divided by x squared plus 2 over x squared over x squared over x squared minus 1. We'll take the limit of that. From here, I can simplify. This is 3 over x plus 2 over x squared over, this is, I forgot the x squared there. 1 minus 1 over x squared, and you can take the limit of each individual term in the numerator and denominator, and you can see that this one, 3 divided by a big number is 0. 2 divided by a big number squared goes to 0. 1 is 1. Limit of a constant is always constant. And 1 divided by a big number is 0 again. So that gives you 0 over 1, which is 0. So that's the algebraic way to show what is happening way on the ends. Okay, and I can do the same thing for negative infinity, and you get 0 as well. All right, so I'm going to leave it at that. We'll come back and do a few more problems in this section, but this is the basics for this one. So we'll see a little bit of the transcendental, some trig functions, some logarithms. Don't want to say that word too much, right? The logarithms in this class, really, you're going to be happy to see some of them. When we start doing some of the derivatives and stuff, they're pretty simple, nice to work with.